All right, so it's a pleasure to welcome back Francesco Cellarosi. So some of you may remember he was a Duke postdoc here a few years ago, and now he is a tenure track assistant professor at Queen's University in Canada. And today he's going to tell us something about the Central Limit Theorem for odometers and B-free integers.
Yeah. Thank you. Yes, it's a great pleasure to be back. It's my second time back since finishing my time here, which has been a lot of fun. But it's my first time back as an official kind of visit. And thank you, Anush, for an invitation. So I want to talk about the Central Limit Theorem for odometers and B-free numbers. So this is a work that's been done with Maria Avdeeva and Sinai. So the first part I will talk about, the Central Limit Theorem, was done by Masha when she was a postdoc at Queen's since last year, and then we did some of the connection with the B-free numbers comes from a joint work, myself with the two of them and myself with Sinai. So I'll try to talk about that. All right. So I'll start by giving you the definition. So the definition, the setup that we're working with is the following. So I'll fix B, which is a sequence of numbers. Sometimes I will think of it as a set, but for now it will be a sequence. So let's say a sequence of numbers where all these numbers are greater or equal than 2 and integers. So that's my B. And then out of this B, I create the following group. So this will be fixed. So fix. And so I will always keep this fixed. Later on, I will add some assumptions. But for now, this is just a general sequence of numbers. So I will define the following group. So that's the direct product. Let's say K, 1 to infinity, Z. You see, I said Z now. BK, Z. Right? So that's this compact abelian group endowed with the uniform with the Haar measure. So you have uniform measure on each factor, and then you take the product. So it's a compact abelian group. And so I guess I will denote by mu sub G the Haar measure on G. And so on this group, I want to define the transformation. T will be a transformation G, let's say mu G to itself. This will be the odometer defined as follows. Okay, so this will take an element in G, will be written as a sequence. So this will be an element in G will be G sub K, K greater or equal than 1, where each G sub K can range between 0 and B sub K minus 1. So you think of them as congruence classes modulo BK in each in the kth coordinate. And so how is this transformation T defined? So if you have an element in your group with the following property, if GK is equal to the largest element in the kth component for a bunch of them, so if GK is equal to BK minus 1 for all k's between 1 and, let's say, I minus 1, so you have maxed out the first I minus 1 coordinates, and the ith coordinate isn't, so and G sub I isn't B sub I minus 1, then you define T of G as G prime, where again, this is a sequence of G prime K, sorry, K greater or equal than 1, where G prime sub K is defined as 0 if K is less than I, G I plus 1 if k is equal to I, and gi if k is greater than I. So basically, I'll draw a picture. So basically, you look at all coordinates, and you basically want to add 1. But you want to add 1 with carry forward, right? So you add 1, and if you are maxed out in the first I minus 1 coordinate, you add 1, and so you go back to 0, but then you have to record it in the next non-zero coordinate. And, so, and then you leave unchanged all the later coordinates. So just to give you, just to be concrete, if you start with an element that's 0, 0, 0 forever, and then you apply the transformation, you first go 0, 1, 0, 0, and then if you apply the transformation a bunch of times, you get to the point where you have b1 minus 1, 0, 0, 0. And then if you apply the transformation once more, you get 0, and then 1, 0, 0, 0, and so on. Right? So, and then if you do it a lot of times, at some point you'll get to the point where you have b1 minus 1, b2 minus 1, 0. And at the next iteration, you go 0, 0, 1, 0. So you do addition of 1, 0, 0, 0 with carry forward. So that's.
So you read mileage from right to the left.
Say it again.
You read mileage from the right to the left.
Yes. Okay. That's right. That's right. And so if B is the sequence consisting of just one number repeated, B, 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 and so on. So this is basically, this is the classical for Neumann Kakutani, let's say B-adic machine, or also known as odometer. And this, of course, has to do with representation of numbers in base B, and you can think of this as representation of numbers in a variable base, where the units, the tens, the hundreds are in modulo different integers. Okay, so the idea is that this is a dynamical system. So now you have T. Of course, T preserves the Haar measure on this group. So now I want to think of T acting on this group. And this is a relatively simple dynamical system. It's a dynamical system with very low complexity. And the idea is that if you have a system with low complexity, how can you expect some kind of random behavior? And the idea is to try to find a central limit theorem for a dynamical system like that. So I need to give you the setup. Before I do that, I want to somehow mention another couple of incarnations of this dynamical system, and in particular one that one can think of. So another way, so this dynamical system T on G can be realized as the addition of 1, 0, 0, 0 without the carry forward on the inverse limit, let's say J, and here you write Z mod B1 B J Z. So elements in here, this is a subgroup of the product J from 1 to infinity, Z mod B1 Bj Z, but then here when you have sequences here, you have the constraints. So let's call this group H. Elements in H, again, are sequences. So maybe I'll write them as Hj. These are sequences such that H sub j is congruent to H sub j plus 1 mod B1 B1 times Bj, I think. And so the picture here is that, I'll try to draw a picture with B1 equal to 2, B2 equal to 3, and B3 equal to 5, although this is the picture. So in the first case, you have two possible values, 0 and 1, in the first coordinate, 0 or 1. So the first coordinate here tells you if you're 0 or 1 modulo 2. And then in the second, so let's say you're 0 modulo 2. So then here you have to look at things modulo 2 times 3, right? 2 times 3. And so here you have a little tower of height 6. 6. And so if you're 0 modulo 2, then you're forced to be either here or here or here in the next coordinate. And then let's say you're here, okay? And so this tells you that you have 0 in the first coordinate. This tells you that, of all the 3 possible coordinates you have, you're in the second one. So you have a 1 in the second coordinate. And in the next coordinate, you can imagine that you have this little tower that kind of repeats 5 times. And then let's say if you're 1, 2, 3, then you can either be here or in the 3 up here or so on, right? So this is the way it works. And if you think of it again as this compact abelian group, then the same transformation I described over there, it's the same. It's here the addition of 1, 0, 0 without the carry forward. Somehow this is the way the inverse limit works. It's just a picture. Yet a better way of describing it as a map of the interval 0, 1 to itself. So T can also be written as a map of the interval 0, 1 preserving the Lebesgue measure in the following way. So I'll draw a picture. This is a picture called cutting and stacking. So the way you do it, so again, I'll try to do with these 3 numbers as an illustration. So you take the interval 0, 1, you cut it in B1 pieces, in this case 2 pieces, and then what you do, you put this interval on top of that. So here, you take this interval and you place it on top of the other. Okay, so what is the map? The map is literally taking you upstairs. One iteration of the map is go 1 floor up. So this point goes here, which means that this point gets mapped to this point. But the map is only defined right now in this left-hand side, and the on the right-hand part is yet to be defined. Okay? So at the first iteration, you define the map on a fraction of the space. The other fraction of the space is not yet defined. But then once you have this thing, so maybe I'll copy it down here, then you divide this thing into B2 pieces. Okay, so let's say 3 pieces in this case. And then you cut and stack. You take this piece, you put it on top of this, on top of that. So here you get a picture that looks like this. There should be 6 of them. So this goes on top of that, which goes on top of that. And so now a point is mapped literally up. And then only this last piece of the space, which was somewhere here, is yet to, over there the map is yet to define. And then you keep doing it, okay? And so the way you cut in B1 parts in the first generation, B2 parts in the second generation, B3, and so on. And of course, if you think of them as always cutting into B parts, you're just writing the representation of a number in base B. That's literally what you're doing, okay? And so if you think about it this way, you can imagine that a number y in the interval 0, 1 can be written, I'll use some abusive notation, as 0.y1, y2, y3. So it's like a decimal expansion, except each yi belongs in 0 bi minus 1. Okay, so I'll think of this as a base B representation. And here again, you can identify this with a sequence y1, comma, y2, comma, y3, and then you can just do T of y equals y prime, where y is thought of as a sequence y1 to the y2 and so on, and y prime is y1 prime, y2 prime, and so on. And you use literally the same rule as here. You just replace the g's with the y's. Okay. So that's another geometric way of thinking of these dynamical systems. Okay.
So these are
Yes.
0 and 13.
Yes.
But how do they're not isomorphic to each other in general, right? For different choices, or they're
We fix the sequence. So there are
for different sequences, they're not.
they're not. They're not.
Do you see it from spectral properties?
Spectrum is the best way to see it. Yes. I'll mention the spectrum at some point. Yeah, so we fix this. We fix the B. Okay, so all right. So let me give you the statement of the theorem. So, but these three different representations are the same, and there will be other things that are equivalent. So I'll prefer to work on the interval 0, 1. But no, it's all equivalent. So I'll work on the interval 0, 1. So I'll give you the theorem, which is the following. So there is some technical condition on the choice of the sequence B, and it's the following. And I'll tell you an example where that is certainly satisfied. Suppose there exist two constants C and epsilon positive, such that for all sufficiently large n, you have the following inequality. So let's say the sum I from 1 to n of the bi's to the power 4 is less or equal than constant, n to the power minus a half minus epsilon, so it's small, but then you have this, which is big, I 1 bi squared. So there is some growth condition essentially on the b's. Then for every t in the real line, so you have the following central limit theorem. So here is the statement. So maybe I should define over here, before I give you the statement, I should define what kind of observable, what kind of functions do we look at under the iteration of the transformation. So here I will denote by f sub y. This is simply the indicator of the interval 0, y. Okay, so that's a function in the interval 0, 1. And of course, this function has integral equal to y. So at some point, I will be subtracting y, and it's just to make things centered, so to just center my random variables. So I will look at the following. So I will look at I start at 0 in my interval 0, 1. I could change the point, but then things become more complicated. And then I look at the trajectory of 0 under my transformation. And then I ask myself, does my orbit hit the interval 0, y? So right? Do I enter the interval 0, y? And then, so this is a random variable, let's say. I mean, nothing is random yet, or possibly y, but I'll be more precise. So that's why you subtract y's to somehow make things centered, and then you sum I from 0 to h. You should think of h as a large number. So this is like a Birkhoff sum, like an ergodic sum, right? And then you want to be able to subtract some expression and divide by the square root of some other expression. I'm filling things in slowly. And then basically the probability that this suitably rescale center and rescale random variables is less than t, you want this probability to converge to the Gaussian, corresponding CDF of a Gaussian, which will be, I'll denote it by phi of t, which is 1 over root 2 pi integral minus infinity to t e to the minus u square over 2 du. Okay, so how do I mean by random here? So what I'm going to try to do is I want to randomize the y. Okay, but then I also want to randomize the endpoint of this. So you could think of taking n here and then letting n live in an interval 1 to h, an interval in the integers, and sample then with uniform probability. Or, which is better, I'll just keep the h here and I multiply h by z, and z now will be, sorry, Patrick cannot see. And z will be randomly chosen in the interval 0, 1, which amounts to the same thing as sampling h uniformly in some large interval. So what I choose here to be random is the pair, let's say y comma z in 0, 1 squared. And here I look at the Lebesgue measure, the two-dimensional Lebesgue measure of this thing. So here there will be some expression that depends on h, some other expression that depends on h, so that when I do this, I get this result. So this is the statement. Okay, so this is not the usual central limit theorem that you expect when you look at.
Just a second. So H is what here?
This is H is going to infinity. Sorry, H is going to infinity.
One moment. So H, I'm still not understanding what H is.
It's the so let's say if H is 100, you look at all possible Birkhoff sums up to 100 or up to 99 or up to 98, chosen uniformly.
You have E of H and var of H. So
I haven't told you what E of H.
okay.
Yeah, so I'm saying there is some expression E of H and some other expression var of H, such that when you subtract and divide by those, you get the expression that you.
So for now, H is a number, and you're going to.
Yes, exactly. Yeah. So and in principle, these E of H and var of H are exactly what you expect from probability theory, which is not very satisfying. So here, E of H is simply the expectation of this random variable once you have this, right? So E of H will be a double integral 0, 1, 0, 1 of that thing. So the sum f sub y of ti of 0 minus y I from 1 to z h dz dy, something like that. Yeah, it will be this. So that's the expectation of this random variable here, and then the variance of h is the same double integral of the same thing. Yeah, exactly. So it's
F of y, z, then this is f.
exactly. If this whole big expression is a function of y and z, this is.
What is that on the left-hand side? Yeah, you sum over I, but.
So you.
Oh, sorry.
Oh yeah, this is an.
You look like a hat.
Yeah, sorry. No, it's an I. It's an I. Yeah, it's okay. Right? And so this is going to be literally the same thing. Fy ti of 0 minus y minus the expectation squared, and then dy dz. Right? So this is not very explicit, but it's you divide by what you have to divide. You subtract what you have to subtract according to probability theory.
So, do you know any more about these quantities?
Yes, exactly. So the way it's stated, B is arbitrary as long as it satisfies this assumption. Somehow there is not much you can say about this thing. But if you give me an explicit set, capital B, I can tell you more about these two expressions.
Oh, okay.
Because this is just written very generally, right?
Anyway, you can do a little bit for BD right away.
Yeah, no. So something can be written down. So let me give you the example that somehow motivated the whole thing for us. So if you k is fixed and it's greater or equal than 2, and then you look at your set B, which is the set of p to the k, where p is prime. So these are kth powers of primes, for example, squares of primes. In this case, so all these satisfy, let's say, the assumption, this condition here. They all satisfy that assumption. And in the particular case, you get exactly how this variance grows. In this case, the variance of h. So I use the symbol to denote that it's bounded above and below by constant, and then I'll write the expression. So this will be e to the power, so constant e to the power 2k plus 1 times log h times 1 plus little of 1 as h goes to infinity. So you can think of this as, imagine that this and the log cancel, so some kind of log h expression up to constants above and below.
And E of H?
I didn't write it down.
Can you try a similar thing with a Poisson process? And usually it's actually done quite often, right? I mean, if you have independent random variables, you have this compound Poisson process where you do a point process in the sum.
Yes.
And that's a natural candidate, and they, in that case, they have some Independent random roots, you have very nice results.
Yeah, the problem is that these are not independent.
I
These
know,
are
but
strongly
have
dependent.
you tried doing a Poisson process?
In H?
Yeah, in ZH.
In ZH, no. We have not.
Just a random integer.
Uh-huh.
And you usually do the family, you can use these birth and death process, right?
Okay.
You randomly sum up with a person identity.
I see. No, we haven't thought about it.
That's a very canonical choice if you come from the independent side.
Uh-huh.
And could probably provide you enough randomness, because I have the feeling you have to randomize your sums.
Yeah, so somehow we have to simultaneously randomize the interval where you land and this.
Right, but this would
randomizing his sum. Or
Z is randomizing your sum,
Yes.
and you could think of other random variables there,
Yes.
which are sufficiently random.
That's right. So one thing that I should mention, so this whole enterprise is done for other dynamical system with the same kind of low complexity, like irrational rotations of the circle. And in that case, you can even fix y. So you can fix y and only randomize in z. But there, maybe I'll just.
No, I understand what
So
you're
when you
saying.
say low complexity, you mean like...
I can write down what I mean.
Zero or something like that?
And these are zero entropy dynamical systems. So there is no mixing, not even weak mixing. They are very rigid systems. So to exhibit...
I mean, they still sort of transitive or minimal or whatever?
Yes.
Yeah.
So these are example of aperiodic dynamical systems. Yes. So let me give you somehow. Why should one at all expect a central limit theorem, right? So why should the central limit theorem even hold? So somehow historical motivation, let's say. Although this was not our initial motivation, but motivation. So let's say analogy with rotations. Okay, so if you take alpha, which is irrational, it's irrational, and then you rotate by angle alpha. So this is just a fractional part of x plus alpha, modulo 1. And so you can rewrite that where instead of your dynamical system T, you have your rotation. And so there is a beautiful theorem by Beck. I forgot to write down the year. I think it's in the 90s. So if alpha is quadratic irrational and beta is rational in the interval 0, 1, then there exist two constants, C1 and C2, positive, depending on alpha and beta, such that when you look at the Lebesgue measure of the z's in the interval 0, 1, such that the sum I from 0 to z, let's say, let me use h again so we don't get confused, f sub beta of 0 plus n alpha. So let me write here. So this is the orbit of the point 0 under the rotation, okay? Minus c1 log n divided by the square root of c2 log n, less or equal than t. This converges as h goes to infinity to exactly the distribution function of the Gaussian. Okay, so this is somehow, so here I forgot to subtract beta. Right, because again, this f beta is the indicator of the interval 0 beta. And earlier versions of this result was actually averaging simultaneously over this and over beta. Okay, but you see, if you average over beta, you're not going to catch this rational behavior. Right? So you can try to fix beta or average over beta or some combination of that. So there has been a lot of progress when it comes to rotations because you can use not only results from dynamics and renormalization and combination of geometry and renormalization, but also you can do Diophantic analysis. So there has been lots of work. So there's been work of Dolgopiat and Sarig, and then Avila, Dolgopiat, Doriev, and Sarig, and then Bromberg, Ulchigrai. All these people have worked on generalization of Beck's result, where you can do several things. You can try to make this true for not just the initial point 0, but for an arbitrary initial point, let's say x naught. You could try to do it not for just beta rational, but maybe you can try to some other betas. And so I think the most general version, they deal with alpha, which is badly approximable, which includes the quadratic irrationals, and beta, which is badly approximable with respect to alpha. So there is some kind of affine Diophantic condition, and this provides a full house of dimension 0 Lebesgue measure set of parameters, sort of thing. Okay, so in this context of rotation, a lot of work has been done, but in this somehow more somehow dry, here there's less geometry, there is less Diophantic analysis that you can do somehow. In this case, we believe that in principle this can be done by removing the average over y, but then you have to tell me what y satisfying this is, right? And so we don't know that yet. And
this switching 0 to an arbitrary point, like how much more involved is this?
it's just a technical working out, yes. So there should be no difference between 0 and another point.
Yeah,
But for example, the way we or Masha is able to compute this variance, this uses some heavily that we start at 0. In principle, you can do it starting not at 0, but then it becomes just more messy. It's literally just pages of computation. But there is nothing substantially different going on. So I should say that this result, so the theorem generalizes something by Levin and Merzbach in 2003, who proved this very theorem where they did it for B equal to B, so somehow the base B odometer. And they also have error term. So you could take this thing, subtract this, and see how big the difference is. And their error term is of the size log n to some small negative power, like I think 1/7. And we believe that somehow their whole strategy can be reapplied in our setting, but we just haven't done it. And somehow get an explicit error term estimate for that case.
But this depends on
This is H, sorry, yes.
This depends on B.
Yeah, the implied constants, yes. So for B, I think, so the implied constant depends on B. I think they write log base B, and there is some other constants there,
But
yes.
your BIs are not bounded.
Exactly, so we haven't done it. So perhaps that assumption star that we have is enough. Maybe you need to throw in more assumption to be able to control the error term. We are not claiming anything about the error term, but I'm saying that in principle, if your BIs are not growing maybe too fast, you can come up with an error term like that. So again, it's just a matter of...
Or your error term might depend on more than the 4, so you get 8 or...
Exactly, so yeah, it really depends. So we haven't done it, but we think that it can be done. I don't think there is any some substantial obstruction. Okay, so this is what I wanted to say. Let me keep track of time. Good. So I want to say a few words about how one proves something like that, and then somehow move on to a motivation, or somehow our motivation for studying something like that. So maybe I'll write down there. So the idea of the proof, is the following. So you do the following. So if you give me a real number y, in the interval 0, 1, which again this will be the y that's in the statement, using again this idea that I explained before, you can write y in base b, where b is this variable kind of base. Right? So you can write y as a sum. Maybe I'm using the wrong letter, doesn't matter. So you could write it as y sub I divided by b1 to the b. So maybe I'll use j here. Right? So this is the same that, imagine that b is 10, and they repeat 10, 10, 10, 10. So this is like writing a number in base 10. And your digits are between 0 and b j minus 1, as usual. So you could write a number, and we don't care about rational numbers that may have more than one representation. Almost every number has a unique representation. So we have this. So out of y, we get this coefficients yj's, and I will also denote b1 times bj as capital Bj, just for convenience. Right, and the idea is that when you take y uniformly random on the interval 0, 1, then you get the coefficients that are uniformly random in each of them in their interval. Like when you take a number that's Lebesgue random on the interval 0, 1, then the digits base 10 will be 0 to 9 with probability 1/10, 1/10, 1/10. It's literally the same, right? So you can see how the choosing the number y random reflects the distribution of these coefficients. Okay? It's literally like when you do base 10. And similarly, once you have n, and this is some of the more interesting part, when you have the number n, which you should think, so maybe I'll write here. So you should imagine that I'm picking my number n uniformly at random in this interval 1h, uniformly. So this is a discrete set, and the way you do it, you can take n. And you could also write n in this base, right? So I'll use c's for the coefficients. So you could write this as cj, j from 0 to infinity, well, not infinity, but say little n, of the b sub j. But now the c sub j is between 0 and b sub j plus 1 minus 1. You have to, yeah. So, right, and so somehow there is a relation between capital N and little n. If this was literally writing number in base b, this would be the log base b of capital N, maybe ceiling or floor, one of those two, right? Here, somehow n is more implicitly defined in terms of capital N. Okay, so exactly. And so you can imagine that instead of writing n uniform in here, I write n as z times h, where z is a uniform random variable on the interval 0, 1. Right? It's uniformly distributed. So it's exactly the same. And as before, every time I choose z random in the interval 0, 1, I'm really choosing these coefficients random. Again, uniformly random in the corresponding interval. Right? Okay, so now choosing those two numbers random jointly is like choosing this coefficient y and c's. Okay? And then what do I do with them? The key is to be able to break this sum that we care about. The one that I just erased, yes, I know. The idea is to take the, maybe I'll rewrite it. Okay. It's here I'm using a different letter for the index. I don't know. You have this sum f sub y t to the L of 0 minus y. So let's say this is the sum that you care about. Okay. The idea is to rewrite the sum as a sum I from 0 to little n, capital N, little n, those two, of some random variables, xi. And xi can be written down explicitly, and it's just a combinatorial argument to somehow break this down into pieces and arrange them. So this is the sum over di from 0 to ci minus 1. Ci's are the same as over there. And then here you take minus this real number that you write yi plus 1 over bi plus 1 plus yi plus 2 divided bi plus 1 times bi plus 2 plus da. So you have all the products in the denominators, starting with bi plus 1, bi plus 1, bi plus 2, 1, 2, 3, and so on. So we have this infinite thing, plus, maybe I'll write it here, the indicator of whether what I'm about to write happens or not. So it's 0 or 1, depending on whether d sub I so d sub I is my index. Again, b sub I plus yi plus 2, bi plus 1. I probably missed the plus 1 here. So plus 1 I plus 2, and so on. So this is a real number that I'm constructing starting from the I plus first integer and using as digits di and then y. So I test whether this real number is less than the corresponding real number with ci's everywhere. Ci plus 1, bi plus 1, ci plus 2, bi plus 1, bi plus 2, and so on. So you see, I take those numbers, the c's and the y's, I build this thing, and I'm just adding. So this is a number between negative 1 and 0 with a minus sign, and this is a plus 1 or 0. So I'm just adding a bunch of numbers between 0 and between negative 1 and 0, but negative 1 and 1, something like that. Yes. So I'm just adding these numbers, and this is somehow this is a key lemma, but it's kind of messy to write it down.
So the first sum is at worst negative 1.
Yes. Yeah. This. I'm just.
These are coefficients.
Yeah, those coefficients. These are the coefficients that are coming from there. Okay.
So you're splitting up your interval from 1 to n in certain pieces, I guess.
And now instead of working on this, I work on this sum. So this is a perfect identity, and the idea is that the larger the n, the larger the little n, right?
You should think of it as a log of
Exactly. You should really think as little n as log base b of capital N, except the base b is a varying base, right? So the idea is to do a couple of things. First of all, truncate. Okay, so the idea is that you truncate, so you work with CIK, where it's the same, except the dots you see here, here, and here are replaced by ... plus something divided by bi plus 1 times bi plus k. So you truncate all the expression you see here. Instead of going all the way down to infinity, you stop at the product that has k terms. So you truncate here, here, and here. So you just deal with rational numbers, essentially. Okay. So you truncate this k, this expression where k is to be chosen, and as you may guess, so here you choose k of the size log of n. Okay, and so that's the first thing you do. And now that you have this sum, I from 0, ci, comma k up to little n, then what you do, now you break this down into pieces. And so the picture now is like this. So now you have 1 to n. And then what you do, you create these relatively long but also relatively short blocks separated by a very short gaps. So the blocks that I'm coloring are the same length. So now I'll tell you what this length is. So the idea is that to have these things are, so these gaps are of order log n. And these things are of order essentially square root of n, but you have to give yourself, I think, a little bit of epsilon, up or down, I forgot. So these are of the order n to the 1 plus epsilon over 2. And if you do it right, and the sum, so the sum, so this is, let's say, so this is j equal to 1, j equal to 2, j equal to 3, the j equal to some number that we call theta 1, and theta 1 is essentially n plus k over theta 2 minus 1 flooring, where theta 2, this is theta 2. Okay. So the idea is that on each, so you have these blocks, and then you call zeta sub j the sum on this interval. So let me call this delta sub j, these blocks of length, of this length, essentially square root of n. So you do j in, so let's say I in delta sub j, and then you have the ci k, yes, like that. So after you truncate, then you look at the sum of the truncation in these large chunks. And so you have 1, 2, 3, essentially n over square root of n of them.
Whatever the letter is, something letter?
The zeta sub j, zeta sub j.
So the letter j
Denotes there is essentially square root of n of them. So you have the sum in these blocks. And by having truncated things properly, so basically the digit expansion of numbers that come from here and from here, they do not overlap because I've chosen this k to be some of the truncation here. Now these random variables are truly independent. When you go from here to here, these are truly independent. These are 100% independent random variable. This method of breaking the sum into that is called Bernstein.
Because you say different randomization comes from more independent sides, so like he's approximating.
I'm approximating these random variables by truly independent random variables.
I think then you can probably replace the ZH by other random processes.
Yeah, I'm sure that's possible.
How do they become independent now? Can you explain why?
Because somehow these CIs, if you truncate them here, so you call them CIK, the digits that are involved do not overlap. The indices of the digits involved in the description of CIK and CI plus 1k, here and then, these digits may have something to do with this, and these may have something to do with those, but then you kind of separate them enough that they literally don't talk to one another. They have no digits in common. Yeah, and here you literally truncate it. You have a sharp cutoff there. Right?
Oh, I see. Yeah.
So this is a classical method in probability when you deal with mildly dependent random variables. And then, so the idea is that now these random variables are independent, and then you prove a central limit theorem for these random variables. So the idea is that, so here we use the Lyapunov version of the central limit theorem. So what you do is the following. You take this random variable and you center them. So you take zeta j hat, which is zeta j minus the expectation of zeta j. Okay, so you center these random variables. And then the idea of the Lyapunov condition is that if you can control, so let me call S sub n square. So this would be maybe S sub n. Yeah, not sure if n is the right letter. I think it's S sub theta 1. So here, this sum that I'm dealing with is now the sum of the zeta j from 1 to theta 1, and theta 1 is morally square root of n. Okay? So now if you have each of them as a certain variance, now they're independent, so the variance of the sum is the sum of the variances, and this is the variance of this sum, and this will become the sum of these variances, j from, yes? Theta 1. Theta 1 will...
You said, yeah, theta 2 is morally square root of n.
And theta 1 as well, because it's n over root n.
Yeah, okay.
Okay, yes. Right, so theta 1 is the number of blocks that you see up there. It's a bad choice of the letter. So here you look at the sum of the variances, and these variances can be controlled. And so the idea of the Lyapunov version of the central limit theorem is that if you can compute this limit of 1 over Sn to the power 2 plus delta, so you give yourself a little more exponent than 2, and then the expectation of this centered random variables with the 2 plus deltath moment of this thing. And then you take a sum, which I forgot to write here, j from 0 to theta 1 again. If you can control this and make sure it goes to 0, then you're done. Okay? And with this, you can do it, and we do it using delta equal to 2, which is basically we're able to directly, explicitly control the fourth moment of these things.
Yeah, but we had an assumption on the fourth moment.
Exactly, and that's exactly where...
Plus epsilon moments, then you would have to change.
Exactly. So that's precisely where that assumption came in, and we are happy enough with that assumption because we were working with this kth powers of primes, which was our initial motivation, right? And so you prove the central limit theorem for the truncated approximated one, and then you control all the differences, and all the differences can be controlled very easily. And if you're happy with little o of 1 sort of things, then it's easy. If you want more control on the error term, then you have to work hard. And if you are curious to see why we cared about this thing, just ask me and I'll tell you. I'll stop here. Oh, sorry, yes.
So you were doing this approximation, but you have to somehow handle the cutoffs, right?
Yes. Yeah, you have to make sure that what you have added and what you have subtracted and added somehow is all small. And those are, I don't know, Markov inequalities and yeah, standard probability. There is nothing fancy there. There is literally nothing fancy there. It may be hard to like do the bookkeeping of all these things, but there is nothing fancy. Yeah.
All right. Thank you very much. Okay. Any other questions for Francesco?
Well, maybe now you can tell us about freeness.
In a minute, yes. Yes. So the idea is the following. So you do this. So you look at mu b of n. It's like the square of the Möbius function. So this, mu square of n is 1 or 0, whether the number is whether n is square free or not. From number theory. And so here it's the indicator of B free numbers. B free numbers were invented by Erdős, and it's as a generalization of square free numbers. And so here you basically look at this sequence of zeros and 1 that tells, so is this number B free or not? And B free means that every B in B has the property that B does not divide n. That's what it means to be free, to be B free. So you look at this sequence of zeros and ones, and the theorem we proved with Sinai, and then there is other versions of this by Lemanchik, Delarue, and I'm drawing a blank on the name. So this theorem says that this sequence, mu b of n, as a sequence of zeros and ones, is a typical realization of a pure point spectrum stochastic process, which implies in particular that this dynamical system, this stochastic process that somehow generates this sequence of zeros and ones, you can imagine kind of a Markov chain that spits out a binary sequence. This is a typical realization of some dynamical system. And this dynamical system has pure point spectrum, which implies zero entropy, no mixing, not even weak mixing. So now, and we can write down this dynamical system explicitly using, there's at least 3 equivalent ways of doing. There's a way using an approach by Sarnak and so on. But this dynamical system, because it's pure point spectrum by Halmos and von Neumann, it's isomorphic to a rotation on a compact abelian group. Precisely the addition of 1, 1, 1, 1, 1 on G. Not the 1, 0, 0, but this one, which is also isomorphic to all the ones I've mentioned before. And then we had the question, can we find a CLT for this particular rotation on ergodic rotation on this compact abelian group? And the answer is yes. The problem is that now this nice observables, the indicator of the interval 0, 1, after you transport the theorem into this setting, these are not nice intervals 0, 1 anymore, because the isomorphism transforms this nice solid interval 0 y into fat Cantor sets. And so we are able to prove a central limit theorem for this dynamical system that came out of some number theoretical question for randomly chosen fat Cantor set, visits to randomly chosen fat Cantor sets, because the y was random, which was the length of this thing. So after you do the isomorphism and you bring it here, the isomorphism destroys the nice structure of the intervals. They remain positive measure, actually measure
So
y.
what do you mean by that? Just some positive measure?
Positive measure Cantor sets, and if you look at the visits to a positive measure Cantor set that's randomly chosen jointly with the length of the Birkhoff sum, then we get a central limit theorem. We wanted to prove the central limit theorem for a different observable, but we couldn't, because proving that would have given us information on the statistical properties of this number theoretical sequence. But instead of proving that central limit theorem that we couldn't, we did it on this family of fat Cantor sets. So that's where the connection was.
All right. Well, thank you very much again.
Thank you.